Hello, Math 8 students. This is Open Up Resources, Unit 2, Lesson 2, Circular Grid. We are going to be talking about dilating figures, and we're going to be using a circular grid. With that in mind, take a second and look at this image and tell me, what do you notice? What do you wonder? Online learners, pause the video to give yourself a chance to look at that, write down the things that you notice and that you wonder. Okay, we're back. Let's listen to our in-person students. Please tell me some things that you noticed. Xander, what did you notice? I don't know what you mean by that. What do you mean they're boxes? I'm not seeing it. Can you show me what you're talking about? I see circles, but I'm not seeing the boxes. What do you mean by them? Oh, you mean like this guy. Well, you don't know what I'm talking about yet. You just said yes. Hold on. Let's wait for this to work. Like that? Okay. So even though you see circles, you also see some sort of I'm going to put quadrilateral in quotation marks because it's obviously not a quadrilateral because, as Xander pointed out, it's curved. Okay, what else do you notice? Zeta. Very great observation. This point in the middle where everything meets together is the dilation center. Center point is center of dilation. Garrett, what do you notice? You also see tiny, and I'm going to do the same thing. I'm going to put triangle in quotations because are they really triangles? No, because they're curved. Let's see those triangles. Like this right here. But it's not really a triangle because it's curved, but you kind of see something there. Okay. What else do you notice? Circles, thank you. That's kind of a big deal. We see a bunch of circles. Zeta. Are they, what do you mean by going down? Because they're not going all straight up and down vertically, right? They're like cutting through. Yep. Garrett? Good, and they're going through that center of dilation. Lines cutting through the circles. And the center. Okay. Anyone else notice anything? This has come up in every class. I'm surprised you haven't said it. What does this look like to you? A spider webs. I've heard students say that. What else does it look like to you? Cole? Okay, I can see candy corn. White, orange, yellow. Okay, Garrett, what do you see? Dartboard. Looks like a target. Lucas. Radar. That's the one that I was waiting for. Does it look like a radar to you guys? Okay, next. This is not observed, but it's something that needs to be pointed out. So eyes on the screen. I want you to notice something. I'm going to help you notice it. You know how a circle, how we've talked about it, how that's 360 degrees? I want you to use that. Tell me what this angle is going to be. You could use a ruler, but a ruler's not going to help you tell you. You could use a protractor, but there's something else that you can use. It's called your mind. Yep. No tools really needed besides your mind. Parker? 30-degree angles. Full circles 360. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those angles. What's 360 degrees? Divided by 12 pieces? Yeah, you could go even simpler and make the math even easier for you. This is 180 degrees because it's a straight line. And you can also see that this is 90 degrees. And 90 degrees split 3 ways is 30 degrees. Okay, let's quickly go over some things like, what do you wonder? Let's make this happen quickly. I'm only going to take maybe 3 or 4 responses. First one's up. Cole. Are they divided equally? And I've already answered that one, right? But you were wondering in the beginning, are they divided equally? Lucas, what are we going to do with it? Zeta. Good. Parker. Why circles? Oops. And last one, Xander. Yep, we have this. What are we going to do with this? This came up in other classes as well. I'll wait. This came up in other classes as well. The title of this is Circular Grid. How would we graph on a circular grid? How do we graph on it? That question will be answered in about 11th or 12th grade. However, to kind of preview it, because this little bit of information we do need to know, this is, we needed to know the 30 degrees because we use it to measure angles, part of it. Okay, but I also want you to observe this. These are all set circles with the same center right here. So this circle has a radius of 1. A radius goes from the center to the edge of that circle. P.S. You did learn this last year if you ever watched any of my videos. So this is a radius of 1. What would this radius be? 2. And this radius would be? Exactly. So you can see how we would measure at least how big that circle is. So I'm going to select a point and I want you guys to tell me what circle it lies on. You'll tell me what circle it lies on by saying the radius is whatever it is. Okay? This point right here. That was quick. A few of you, Xander. Double check. I know it's hard to tell because you're far away from the board. Fix it. What would it be? It would be radius 4. Good. And here's how you're going to be graphing this using your future 11th and 12th grade knowledge. Okay? If I wanted to graph this point right here, what radius is it on? 4. So we would graph points like this according to the radius and the angle. So the radius comes first. What radius is it on? It's on a radius of 4. What's the angle? This would be an angle of 0. This is an angle of 90. So 4, 90 degrees. It's a normal grid, but circles. Here's the other difference, just to really hurt your brains a little bit, give you something to stretch towards. We don't measure degrees in angles when we use this kind of, I said that weird. We don't measure angles in degrees. We measure angles in radians, which is something you will learn about in 10th grade. So we would really write it as 4, pi halves. Yep, that's your future. It's coming. Let's come back to 8th grade though. Let's quickly review all of the things that we should know about dilations after our lesson last time. A dilation is a transformation that produces scaled copies. So we have heard this word transformation before. We've talked a lot about transformations. In the past, we talked about specifically rigid transformations. Do you see this information on the board? Should probably maybe like write it down or something. I don't know, just a thought. So we talked about rigid transformations. Specifically, we talked about translations, rotations, and reflections. And when we talked about these rigid transformations, we also understood that these rigid transformations preserved angle measure and distance. Therefore, they produced congruent figures. Nothing new there. That's basically a summary of all of Unit 1. So now we're looking at dilations, and a dilation is a transformation that produces a scaled copy. So when we look at dilations, we have angles preserved. Angle measures are preserved. I'm going to fix that. Angle measures are preserved. That means they stay the same. That's similar to the rigid transformations. But here's what's different is side lengths are scaled up or down. So rigid transformations kept the distance or the side lengths the same. Dilations are not going to keep them the same, which means they are not producing congruent figures. Although they have the same angles, they will have different side lengths, so they will produce non-congruent figures. Dilations do require a center of dilation, and they do require a scale factor. So, a new type of transformation, one that is not rigid. And now let's move on to our next activity. Before we get started on our next activity, there's some more that we need to review, and this should also be written down. This is a line. We talked about this in the last unit as well. A line, you might remember, is infinite. Even though I stopped drawing it here, I used an arrow to show that it continues infinitely on in that direction, and I drew an arrow here to show that it also continues infinitely long in that other direction. We also talked last unit a lot about segments. A segment is just a piece of a line. Notice that this segment does have an endpoint. You can say it has a start and an endpoint, but really mathematically we call them both endpoints. Because we can see specifically where it starts, where it ends. It doesn't continue infinitely. It stops where I stop drawing it. And now we have kind of a combination of each of these. This is what we call a ray, where a ray has an endpoint, a specific place where it's going to end, or if you want to consider it where it starts, but it continues infinitely on in the other direction. Okay, so whenever we're drawing these, we are going to be drawing rays today, which means that we will have an endpoint and we will have an arrow on the other end. And whenever I draw rays, I always want to draw them at least to the edge of that diagram. I can't draw it infinitely, but I am going to draw it to the edge of the diagram. Now you have everything you need to answer these questions. This larger circle D is a dilation of the smaller circle C, and P is the center of that dilation. P is the center. So we are going to be drawing 4 points that are on the smaller circle, not on the inside, but on them. You can draw them wherever you want. Here's where I'm going to choose to draw them. There's my first one. I'm going to call that one E. Here's my next one. I'm going to call that one F. I'm going to do this one in the middle, just to be different. G. And I'll do this one over here. We'll call that one H. It says 4. Draw 4 points. And now it says draw the rays from P, so that tells us the endpoint, through each of those 4 points. So here's what I'm going to do. I'm going to draw from P through E, but since I'm drawing a ray, remember I said draw it to the edge of that diagram. So I'm going to go past E all the way to the edge of the diagram. And I'm going to turn those into rays by putting an arrow at the end. I want you guys to do that as well. Continue that with all of your points. F from the center point P through F and all the way to the edge of the diagram because it's a ray. From P through G and all the way to the edge of the diagram. From P through H, all the way through to the edge. Make sure they're raised and they have those arrows showing that it extends on even past our diagram. Okay. Now it says label the points where the rays meet the larger circle, E prime, F prime, G prime, and H prime. So this is what that means. We drew the line that went from the center of dilation through E and beyond. So when I go beyond, you'll see that that ray goes to circle D and even beyond that. That means where that ray and circle D intersect, that's going to be labeled E prime. Continue on for each of your points. Here's my F. The ray continues on until it gets to D, so that's going to be F prime. G continues on. This point here is going to be G prime, and continuing on, H prime. So what is the purpose of this activity? What are we expected to learn from this? Remember, it started by telling us that this larger circle is a dilation of the smaller circle. What that really means is I can take a circle, there it is, now it's circle C, and I'm going to continue to dilate it until it becomes circle D, right? But I want you to think about what happens with each of those points. Look at where E is. When it's dilated, where does E go to? All the way up there. And that's what we have done, is we have just taken and figured out where each of the points on the original circle ends up in that dilation. I want you to understand the process and just how important that process is, because now we're going to be duplicating that over here. Okay? What we did is we started with a ray, the ray that went from the center past that point and beyond. And that's how we were able to determine where that new point was going to be. So let's take a look at the next one. This is a quadrilateral on a circular grid. And we're going to dilate each vertex of polygon ABCD using P as the center of dilation and a scale factor of 2. And then it tells us how to label it. So let's make sense of that. We can see once again, P is the center of dilation. Okay? And normally what I would do is I would draw a ray that goes from P through A and beyond. But do you see how that line was already there on that diagram? Yeah. So I'm not going to take the time to do it for everyone, because I just want to point out that normally we would take the time to go from the center through the vertex and beyond. But those lines are already there. So I'm going to save some time by not going through that process. Okay? But make sure you're paying attention to the line that's on there, because that's going to be important. And now using the scale factor of 2, that means everything is going to be multiplied by 2. So let's start here with A. Notice how far away A is from P. We can count the radius or the units. There would be 1, 2, 3, and 4. So A is 4 away from P. I'm going to write that down. But with the scale factor of 2, that means I'm going to multiply the 4 by 2. In doing that, I get the number 8. So how far away is A prime going to be? No. 4 is multiplied by 2, so it's going to be 8 away. Let's count that out. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Make sure that you are paying attention to what happened. Again, focus on this ray. I'm going to do it just this one time. Focus on that ray. Do you notice how A and A prime are on that same ray that started at P? And so that's what you need to be paying attention to, because pretty soon even these lines are going to be going away. So we need to know which direction it's going, and it's going just further out, but in that same direction. Let's move on to B now. How far away is B? 1, 2 away. So let's remember that. That means that this distance of 2, B is 2 away, but with the scale factor of 2, that means I'm going to be doubling that distance. So how far away is B prime going to be? 4 away. But it's going to be 4 away going in the same direction. So 1, 2, 3, 4. There's B prime. Continue on, figuring out where your C and D points are going to go. C prime and D prime. 1, 2, 3, 4, 5. So I'm going to write that down. 5 multiplied by 2 means that this point C prime is going to be 10 away. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 away. And there's C prime. And lastly, D is 1, 2, 3 away. 3 multiplied by 2 is 6. So now I know where D prime is going to be. It's going to be on that same path, but 6 away. There's that D prime. Now we have figured out where each of those points are going to be. Now we need to make it official. We're going to connect each of those points with nice straight lines. And now I want you to discuss what are some things that you notice about the new polygon. We performed a successful dilation. What happened when we did that dilation? Discuss with your group members. We'll come back together in just a few seconds. All right, what do you notice? Tell me something that you notice, please. Come back to me. Thank you, Zeta. Same shape, but bigger. What specifically is the same about it? Nadia? Yeah, we can't say exactly the same spot, but we can say they're going in the same direction, right? The points are in the same direction as they were before. Let me rephrase that. Callista. They have all the same angles. Here's what we can see. I'm going to show you. Take a look and see. See how those angles line up perfectly? Perfectly? Okay. So that confirms that, just like we suspected, angles are the same. Are the side lengths the same? Obviously not, because you said that they are bigger. So the question is, how much bigger are those sides? Xander? They are 2 times as big. Why are they twice as big? Well, because it was a scale factor of 2. Yep. It's really not too bad. The circular grid can be really helpful for doing dilations. And the last thing that I want you to observe is, do you notice that these lines are parallel? Let's write that down too. Lines are parallel in image, and I'm running out of space. Pre-image. Okay, now, I bet you guys can probably do this next one on your own. We're going to skip 4, just for the sake of time. I want us to do number 5. Number 5 says, dilate each vertex of the polygon ABCD, that was our original one, ABCD, using P as the center and a scale factor of 1/2. So how is that going to be different than what we did last time? Yeah, it's going to be smaller. Garrett? Well, we can divide it by 2, but I want us to get in that habit of scale factor is the number we multiply by. So yes, dividing by 2 is the same as multiplying by 1/2, but let's focus on that multiplying by 1/2. So this distance here from B to P is 2. Multiply that by 1/2, and that's going to be a distance of 1. We are actually going to call it says it here in the directions, we're going to label the image of B as F this time. I know, I don't know why they did that, but we'll follow the directions. F. Continuing on. A. 1, 2, 3, 4 away. 1/2 of 4 is 2, so it's 2 away now. And A is going to be renamed E. C was 1, 2, 3, 4, 5 away, and 1/2 of that is 2.5. That's going to be called G. 1, 2, 3 away, and 1/2 of 3 is 1.5. Man, if only if it were written down or something. A is labeled as E, B is labeled as F, C is labeled as G, and D is labeled as H. Okay, and just like before, we connect them. It's awesome is what it is. Okay, once you're done connecting, quick discussion. What are some things that you notice? Are they the same as what you noticed before? Is anything different? Are lines still parallel? Is the shape the same but bigger? It's smaller. Are the points going in the same direction? Are the angles the same? And are the sides twice as big? Ooh, that's cool. They're twice as small or half the size. Are half as big. Oops. And, uh-oh. That's weird. That one that I didn't want didn't actually copy. Same shape, but smaller. Do you see how cheaty I was that I just copied and pasted? I know you guys can't do that, so go ahead and just put mostly the same as above. All right, we're getting short on time, so let's quickly move on. A quadrilateral and concentric circles. This is different. We no longer have our grid, do we? We just have the circles. It is okay, because think about on this grid how many lines we didn't need. We didn't need this one or this one or this one or this one. And here, they've given us one of those lines. So here it says dilate polygon EFGH using Q as the center this time. And a scale factor of 1/3. The image of F is already shown in the diagram. So look at what they did. They drew that line that went from Q, the center, through F, and to the edge of the diagram. And let's count. How far away was F from Q? 1, 2, 3. Okay? And now I want 1/3 of that. 3 times 1/3 is equal to 1. So how far away is F prime? 1 away. Count again, Garrett. 1, 2, 3. It's only 3. Okay, and so here is F prime. Now here's the process that we need to go through for each of the others. We're going to go from Q, not just to E, but always go through to the edge. Because if I'm dilating bigger, I need it to go past that. Here we're dilating smaller, so it's okay. Now let's count again. What's that distance? 1, 2, 3, and we already did that. 3 times 1/3 is equal to 1. So where is it going to be? On that ray, but on the radius of 1. E prime. Now let's look at this one. Again, I'm going to draw from Q through G. And let's count to see just how far away it is. 1, 2, 3, 4, 5, 6 away. 6 times 1/3 is equal to 2. So I'm going to go in that same direction, but just 1, 2 away, and there's G prime. And for some reason, every time I've tried to draw this segment that goes from Q to H, it doesn't let me go through H. Do you see that? I'm trying. It just keeps bouncing past it. I know. So you guys will have more success than me because you can actually use your straight edge to get through that point. It's not letting me. So I'm going to have to eyeball it. And when I go through this, I see it's 1, 2, 3, 4, 5, 6, 7, 8, 9 away. And 9 times 1/3 is equal to 3. So it's going to be on that line, but 3 away. 1, 2, 3. And since my H is not exactly on that line, I'm actually going to go a little bit higher too. You guys understand, right? Okay, now we performed another successful dilation. Connect those points, forming your quadrilateral. Okay, that was fun, right? Okay, let's summarize. A circular grid like this one can be helpful for performing dilations. Agree or disagree? Was really helpful. The radius of the smallest circle is 1 unit, and the radius of each successive circle is 1 unit more than the previous one. That's why we said this was 1, this was 2, and 3, and so on. To perform a dilation, we need a center of dilation, a scale factor, and at least a point that we're actually going to dilate. Otherwise, what's the point in doing a dilation? In this picture, P is the center of dilation with a scale factor of 2. So P is the center, scale factor of 2 means that, take a look at A. A is 1, 2, 3 away, right? So scale factor of 2 means that A prime is going to be 6 away. So here's that 1, 2, 3, 4, 5, 6. Since the circles on the grid are the same distance apart, PA prime, so that's a point that go, or the segment that goes from here to here. Will someone please close the door? Is twice the length of PA, and that makes sense. 6 is twice the length of 3. Let's move on to our cool down. We're already to our cool down, but that's good because class ends in 3 minutes. Dilate A using P as the center of dilation and a scale factor of 3. So here's P to A. What's the distance from P to A? That's a distance of 1, which means a scale factor of 3. I'm going to be multiplying it by 3, and that means that the new distance is going to be 3. But it's going to be in that same direction. 1, 2, 3, and there is A prime. It does mean it's 2 away from the normal A, but we normally truly don't talk about the distance from A to A prime. Usually it's always A prime to the center, but that is a great question. And now let's do the next point. The next point says dilate B using P as the center of dilation and a scale factor of 2. So this is 1, 2 away. And a scale factor of 2 means 2 times 2 means how far away is this one going to be? 4 away from that center. So 1, 2, 3, 4. Here is B prime. Your homework is the lesson 2 practice problems. That's it for today. Thanks for watching. We'll see you next time.